Hello everyone, myself Akash Dixit, pursuing my BE in Sri Venkateswara College of Engineering, Department of Electronics and Communication Engineering. Today we'll be discussing about the topic on Thevenin's equivalent circuit and superposition theorem. The contents of today's topic are Introduction to Thevenin's equivalent circuit and superposition theorem, the numerical questions, solution to the numerical 1 and solution to the numerical 2. Thevenin's equivalent circuit. The equivalent circuit is a voltage source with voltage Vth in series with a resistance Rth. The Thevenin equivalent voltage Vth is the open circuit voltage at the output terminals of the original circuit. Superposition theorem. Superposition theorem states that in any linear bilateral network where more than one source is present, the response across any element in the circuit is the sum of the responses obtained from each source considered separately. In contrast, all the other sources are replaced by the internal resistance. The, these are the two numericals which we'll be solving in today's video. The first one is based on Thevenin's equivalent resistance and the second one is based on superposition theorem. The first numerical is the Wheatstone bridge in the circuit shown in figure 1 is balanced when R2 is equals to 1200 ohm. If the galvanometer has a resistance of 30 ohm, how much current will be detected by it when the bridge is unbalanced by setting R2 is equals to 1204 ohm. So first we'll find out the VOC. To find the galvanometer current, we redraw the circuit and remove the galvanometer. Using the mesh analysis, we get I1 is equals to 120 by 900 plus 60, which is nothing but 120 by 1500 ampere, and then I2 is equals to 120 by 1204 plus 800, that is 120 by 2004 ampere. Applying Kirchhoff voltage law clockwise along the path 1204 ohm to BA to 900 ohm, we get the value of Vt, that is the Thevenin's voltage. We get the value approximately equals to 95.8 megavolt. And then to find the Thevenin's equivalent resistance, we deactivate all the independent sources and look into the terminals AB to determine Thevenin's resistance as shown in figure 1b. So to find the Thevenin's resistance, we find the resistance of Rab. Here we can see that 600 ohm is in parallel with 900 ohm. So we add these, we find the resistance of these two when it is parallel, and then add with the resistance of 800 ohm and 1204 ohm. We find the value, and the Thevenin's equivalent resistance is approximately equal to 840.64 ohm. Hence, the Thevenin's equivalent circuit consists of 95.8 megavolt source in series with 840.64 ohm resistor. If we connect this 30 ohm resistor, that is the galvanometer resistance, to this equivalent network, we obtain the circuit in figure 1c. This is the figure 1c. The galvanometer current is determined by the voltage by the total resistance, that is nothing but the Ohm's law. We get the value approximately equals to 110.03 microampere. The second one is the superposition theorem. So for the network shown in figure 2, apply superposition theorem and find the current I. So the solution to this is we redraw the circuit and then open the 5 ampere current source and retain the voltage source. The resulting network is shown in the figure. The circuit is redrawn and this major part is taken here and this part is taken over here, and we get the separation of this. The impedance as seen from the voltage source is nothing but total impedance is equal to the total resistance, that is nothing but the total resistance is 4 minus j2 plus 8 plus j10 into minus j2 whole divided by 8 plus j8, and we get the value around 6.01 and an angle of minus 45 degree ohm. The current is nothing but minus J2 by Z, that is the resistance by impedance. We get the value approximately equals to 3.38 and an angle of 105 amperes. Next short the voltage source and return the current source. The resulting network is as shown in the next slide. So I3 is equals to 5 ampere. We apply the Kirchhoff voltage law for mesh 1 and mesh 2 and we get two equations regarding I1 and I2. Solving the two simultaneous equations by the method of matrix, we get the value of I2 around 2.897 and an angle of minus 23.96 ampere. Again, we redraw the circuit as per our convenience. Since IA and IB are flowing in opposite direction, we need to subtract both the current to find the total current of the resistor. So the total current of the resistor would be Ia minus Ib, that is nothing but 6.1121 and an angle of 114.78 amperes. So these two are the numericals discussed today, and hopefully it was helpful for you. Thank you.